Already filled up. No, don't trust me. Let's just throw it away. I can get to you. Yeah, I wouldn't ask for it. No, you would first of all just like set it up. If I asked for it, I'd use this on an 8 for a tray.
Problem set for today. The bomb
That's so great.
Oh wait, no, not hold on.
I got you.
Wait, we didn't use the last name. 17 we did 17 so those 2 8 and I think that did you give us so much space on the back for like 18 like 18 it's like a quarter of paper
Yeah, I was like, I can't see this equals 1. I had such a big chance.
it's so upsetting. Don't say things like that. I already have enough stuff.
I haven't figured what it is.
You should go either opening or closing knife.
You should go every day.
Yeah, come all the time.
Come support us in this direction.
Hi, Kyle.
Oh my God.
No! Good.
Hey, you race.
Oh, yeah.
Yeah.
Oh, I mean, yeah.
Okay, first one. Remember the 4 can be brought up front, which then makes the inside the harmonic. Now, you don't actually have to show them 2 steps. You can just say this converges or diverges. Diverges. For this one, I would take one of 2 different justifications for that. What is it? It's harmonic. If you just say diverges because it's the harmonic series, you're good. If you did the P series direction, you could say diverges because it's the P series with P equal 1, which is less or equal to 1 is the great dividing line. Remember, if P is less than or equal to 1, then it diverges. If P is greater than 1, then it converges. Okay? How about the second one? You say this? Converges or diverges? Diverges because this is a P series with P equal 1/2 less than or equal to. See? You follow? In other words, the terms are getting smaller, but not fast enough. It's getting an infinite large sum. And this, converge or diverge? Converges because it is a P series with P equal to greater than 1. Easy enough, right? Okay. Yes?
So if it diverges, then any integral of it would just go to infinity.
That's a good question. That's today's lesson. Super duper. Okay. So, we touched on this the other day, but we're going to formalize
Yeah, I'm
it.
just gonna come to a plan.
The relationship between integrals and series, and there is a good one here. So, it goes like this. Imagine if you had the area under 1 over x squared, which you know still has asymptotes at the axes, but the square would cause it to get smaller faster than 1 over x does by itself, right? If I start at 1 and continue on forever, then I get an infinite or unbounded region.
You get unbounded.
What? It is, but the region has no upper bound, so it does converge, but it's still an unbounded region. Yeah. Okay, so if I were to compare the true area under the curve to the area using right-hand rectangles with base 1, then I would have these as numbers of importance, right? And if I'm using right hand, then in the subinterval from 1 to 2, I would draw the height at 2. And at 2 to 3, I would use the height at 3, 4, and so on. Those are right-hand rectangles. And are we in agreement?
Yeah.
Cool. Okay. What is the relationship between the true area and the right-hand rectangle area method? In this case. Which one's greater?
Oh,
Actual.
The actual area. So we could say that the right-hand rectangle area of a method is, in this case, less than the true integral value. Now we're working towards, the goal would be to try to make a connection between series and integrals. The right-hand rectangle, the bases are all 1, so we can factor that. Right? And the heights, they are 1 over, should we use the function or go straight to the values? 1 over what squared? 4, I agree. 1 over 2 squared, 1 over 3 squared, 1 over 4 squared, 1 over 5 squared, forever. The first height being at 2. This we can start doing our improper integral work. This is a good review to that. So that's how we would normally start an improper integral. We create a limit. Let's go series over here. Please identify the series on the left. 1 over? And? I'm waiting for the rest of that.
Plus 1 squared.
Oh, okay, if you started at 1, you can say plus 1 squared. Let's just go n squared, shall we? And start it at 2. Although you're right, you could do n plus 1 quantity squared. Sure that. For reasons of my own, I want it to look like the right hand side, so I'm going over this one. Okay, so less than. The limit as a goes to infinity of, the antiderivative is negative 1 over x via power rule. Good. Okay, the left-hand side, I'll leave it alone. The right-hand side is the limit as a goes to infinity of negative 1 over a plus 1 over 1. So we can therefore say that this infinite series is less than 1. Now, less than finite is finite, assuming the terms are, careful now, positive. Okay, I mean, you could go negative infinity and read it on the other side. Less than finite is finite for positive terms, which these are. This can't go to negative infinity. So it has to be stuff between 0 and infinity. It's got to be finite. You with me? Okay. Now that is the idea kind of behind the integral test. You compare, it's not usually all this much work. I'll explain in a second. This is the idea. Would left-hand rectangles be useful in this case? If I did left-hand rectangles, what would that take me? It would be greater than, so the left-hand rectangles would be greater than the true area. And the left-hand rectangles, or the series then, that we get would be greater than 1. What would that tell me about the infinite series? Sorry. True area. So the series would actually take on this. It would just start at 1. Now, what could I conclude from that? This infinite series is greater than 1. Could be infinite, but could it be finite and just bigger than 1?
Yes.
Okay, could be finite or infinite. In the end, then, it's inconclusive. Now, that's going to permeate the direct comparison test. I wanted to kind of lay the groundwork for that. So, less than finite is finite, that's true, but greater than finite doesn't go in, right?
What does the parentheses say? The right bottom.
4 positive terms. To say something is less than infinity means it's finite is only true if you're dealing with it in pocket case. I mean, I could have something negatively huge and it would be less than infinity, but it would be exactly. Okay?
Infinity also.
Yeah, a negative infinity, well, it's still diverging either way, so whatever. All right, say then you compare the area under 1 over x from 1 to infinity. So the curve is 1 over x this time. No, that's terrible. And also this time you're using left-hand rectangles, so is the left-hand rectangle area going to be less than the true area or greater than? Greater than the true area from 1 to infinity. Okay? Oops. The left-hand rectangles, they all have a base of 1, and the heights would start at 1 and then go half and a third and a fourth forever. And that then would have to be greater than the limit as a goes to infinity of 1. That we express the left-hand rectangle area as a series or a sum. N equals 1 to infinity, and the function is 1 over n. Notice we use n, not x. Okay, greater than this limit as a goes to infinity, natural log of x from 1 to a. From that, we can conclude that this series, which we know to be the harmonic series, must be greater than infinity. What does that tell us? This series is greater than something that's infinitely large. The series must be infinitely large. We could conclude that it must diverge because it's greater than something that's infinitely large. That's the idea behind a direct comparison test, to show divergence. Along the same kind of token here, would it have been useful to use right-hand rectangles? Well, right-hand rectangles are less, and that would have led to the series is less than infinite, from which we can conclude no. No conclusion can be made. Conclusion. Okay, now, that's the big idea behind both the integral test and the direct comparison test. Now let's get into the details of each and how you execute the plan. If the rule in an infinite series is the same as a function in an improper integral, in other words, you have this series and the function, like 1 over n squared or 1 over n, is the same, I guess I'll do this, as a series like it, but of course, or sorry, a integral like it, but of course you're talking x's. If those two have the same rule, 1 over n or 1 over n squared, then they must behave in a similar fashion. If they have the same rule, both the series and the integral converge together. Or actually, I don't say it together. That makes it sound like terms. Or diverge. They have to behave in a similar fashion. If the integral converges, then the series that's just like it has to converge also. If the integral diverges, then the series just like it has to diverge. That's going to actually open up a ton of problems for us because we can integrate a ton of different things. We've developed a lot of integration skills, and that would then allow us to take a series that looks like an integral we can do and use the integral test. Before we go to the integral test, you need to be careful. Yes, these both converge or diverge in the same way, but the sum of the convergence is not the same. Okay, they don't converge. The answer to this problem and the answer to this problem, if they converge, they're not the same answer because this is infinite, but this is real numbers. X is continuous, decimals, fractions, and so on. This involves whole number ends, and so they add to the same thing as not true. You with me? They do not, if they converge, they do not add to the same value. Okay, so be careful not to overdo it and say, well, this integral value came out to be 7, so this series would also up to 7. That's not true. All right, so the integral test looks like this. If, first of all, under what circumstances would you use the integral test? Why integral test? I would first say, why not something else? Well, it's not geometric, it's not telescoping, it's not a p-series. So why integral test? Well, I can integrate. If you made that an integral with x's and stuff, how would you integrate? What's the method? Yeah, it's a use of. It's perfect use of it. So you would create a series, an integral. I'm really having a rough day today. I cannot speak. An integral that's like it, but you use x's for your integral rather than n's. 1 plus x squared, quantity cubed, dx. And the goal is to show that, yes, this integral either converges, and therefore the series converges, or the integral diverges, and therefore the series must diverge. After that, for the conclusion. So we need to do our improper integral work. How are these improper integrals going? Okay. We talked about how if the antiderivative is hideous, I recommend you do it off to the side and not change the limits, because on these problems you not only have to change the limits of integration, you also have to change the limit statement too. So if you can avoid having to do that, that's better. This one's not too bad to mentally differentiate, I think. I say that because I have such a high opinion of your skills. What's u? 1 plus x squared. What's du? That's perfect. So what's the antiderivative of u to the negative third? Negative 1/2 u to the negative 2. And that u then would be 1 plus x squared. Do you all see where we're coming from there? Oh, the exponent. You're right. You're right. Sorry. Thank you. Correct. Absolutely. Okay. Are we good? So, evaluating fundamental theorem style. Maybe negative 1 over 2, 1 plus a squared all squared, plus 1 over 2, 1 plus 1 squared squared. What does the first term go to as a gets infinitely large? 0. And what does the second term go to? Or equal? 1/8. Okay. Most important, then, you can see it's a finite conclusion, which is to say that integral converges, right? So our conclusion would be something like the series converges because the integral converges. You don't really need to say parenthetically integral test. You can have about 7 to 8 tests at the end of February. You don't need to identify the test in this case because it's not like any other. They'll know it's an integral. Okay? That's the identity integral test. Are you with me so far? Cool. Okay, direct comparison test I really enjoy because it's got cool logic to it. Would you just, like this part lost people here, so I'm going to change these to n equal. I'm going to start them both at n equal 4, just so I don't get mired in this other little detail that's not important. All right, so we're comparing 1 over n factorial to 1 over 2n. Now, when you do a comparison test, you'll always be comparing an unknown that they ask about to something that's known, a known quantity. And in this case, I think we can all agree that's the known quantity. What is it? I heard geometric. It's geometric with an R of 1/2, which is, so, okay, maybe I overstated it when I said it's a known quantity. Perhaps they're both unknown, in which case you're trouble. So, great. I have this series that's converging, or has a finite sum. I'm going to compare this one I don't know about to it and see where that leads me, right? So factorials are pretty new to us. Today's the first time I think I put one in. They're really important for this year. These factorials will come up in Taylor's series, which is a huge idea in this class, so I want to start getting familiar with it. If we start at 4, then my first term is 1 over 4, okay? Factorial, excuse me. So that is 1 over 4 times 3 times 2 times 1. Then I would then put in n equal 5 and add it, so the next term would be 1 over 5 times 4 times 3 times 2 times 1. And just trust me that I'm expanding them for a reason. Okay? And then I'll do one more. 1 over 6 times 5 times 4 times 3 times 2 times 1. And that continues forever. Now compare that to the exponential, or the geometric series. 1 over 2 times 2 times 2 times 2 is the first thing I get when n equals 4 goes in. Then when n equals 5, I'd have 2 like that, right? Okay, now, we think of exponential as very powerful, and it is very powerful. But how does it compare to the factorial?
First it's larger, but then it gets
For these, yeah, the factorials. So let's go here. This is 1/24 versus 1/16. Now focus on these. I think you'll agree that 4 is greater than 2, and 3 is greater than 2, and so the factorial would weak in terms of the denominator being bigger, which means the terms get smaller. When you look at factorials, they both involve then bringing in another factor. So they're similar in that sense. They both now will have 5 terms. But the new term, compare the new term. This one, every time you add a new term, you're always just bringing in another 2, every time. Whereas this one, you're bringing in something even bigger each time. Every time I add a term in or bring in another term, it's getting bigger and bigger. So because I am getting bigger and bigger denominators here, this will definitely, these denominators are much greater than those denominators. The factorial denominators are much greater than the 2 to the n denominators, right? We know then that our series must be less than the exponential. The factorial gets smaller faster. Now, what would that allow you to conclude about the series 1 over factorial? Why? It's less than this, which is finite. Okay, so we know 1 over n factorial is less than finite. So 1 over n factorial must also be finite or converge. And that's one thought process behind the direct comparison test. I said it in the symbols here. If a sub n and b sub n are two different positive is kind of important, positive term series, and all the terms of the first one are less than all the terms of the other one, and you know that b is finite, then A must be finite. To say this in plain old English, would you say less than finite is finite? That's what we put that. Yes. It could, but it would have to approach zero. It can't be negative because it's a positive term series. And that's why you're right to think that, because that could open up infiniteness on the negative side, and that is a whole nother ball game. Yeah, but it's because of the positive term series. Good question. Okay, so less than finite is finite. Easy enough. Let's show you how this works in action. And on these problems, you'll usually get a series that kind of looks like a known one, like a p-series or a geometric, but the slight difference being that you're adding one or something like that. Now, adding one means it's not a p-series. That is not a p-series. It's not any kind of series. But it's like a p-series, and we're going to compare it to a p-series. That's what makes it a direct comparison test. So the first thing you decide is, what is it like? It's like 1 over n squared. You should never compare it to a series that you also don't know anything about. So you wouldn't compare it to 1 over n squared plus 2, because you don't know that either, right? You compare it to something you know. This is the part that has to be a logical argument. Okay, it's not just converge or diverge, boom. It's an argument. I think you'll agree that n squared plus 1 is greater than n squared. I'm allowing you a little break here, by the way. My professor made me start here. 1 is greater than 0. And then he said, okay, now n squared to both sides. And to me, that's ridiculous. I mean, come on. We can't all agree that's true. Okay, but he said you're supposed to start where any idiot can follow you. And so that's where that started state. So, accepted rules of math. My goal is to set up a comparison, not just between this stuff, but to get a comparison between the series themselves. So now I'm going to work towards reworking this towards they get to the series. So if I take reciprocals, what happens to the inequality? It flips. We learned that in delta epsilon, right? Again, in a pretty logical step, if I have a bunch of terms like this, and every one of them is less than a bunch of terms like this, then the sum of all those terms must be less than the sum of all those terms. Now we know that this is, that says finite, right? The one they ask about is less than finite, and so it must be finite, and therefore we can prove or establish convergence or divergence. Convergence. Yes?
So, do you have to say like that the sum of 1 over n squared?
That's a great question. I haven't said that, and to me, you might be just me pulling it out of nowhere. Okay, that said the conclusion. That's a good question, also. The conclusion. This is the background or your evidence, but now the conclusion. I'm going to play with this a little. I don't like that one. Okay, the series. First of all, the question: does it converge or diverge? Converge. You don't need to say the series in question. The series converges because, actually, let's just say because it is, I want to say it in words, because it is less than 1 over n squared, and here's the part that Cece is referring to, which converges, but you have to say why you say it. Parenthetically, you say 1 over n squared converges because it's a p-series with p equal to n. The one you're asking about converges because it's less than a series that converges, so it must converge. Follow? Okay. They won't do this to you in this book, but sometimes, maybe they might have a problem like this. What if the problem had been 1 over n squared minus 1? n squared minus 1 is less than 1 over n, or less than n squared. I think you agree. 1 over n squared minus 1 is greater than 1 over n squared. And therefore the series 1 over n squared minus 1 is greater than the series of 1 over n squared, all the sums of those terms. Well, that just tells me that the series you're asking about is greater than finite. Well, where do I go from that? But the one you're talking about is greater than a finite number. It could be finite also and bigger, or it could be infinite. It's inconclusive. And you would have to use another test, which you don't know any other tests, so that makes it really difficult to do.
Could you use n cubed because n is most positive n cubed?
To establish n cubed greater than n squared minus 1 would take a little bit harder proof, but you could do that and it wouldn't be bad.
You have to just put in the, like, in delta epsilon proofs, just put another less than
Like-
sign next to the n squared.
Like that?
That's all you need.
Where did that...
On the left hand.
Oh,
Yeah,
here?
so wouldn't it still end up with the same?
This is less than n cubed.
Yeah, but then you still end up with
Yeah,
1
like,
over n squared
I
minus
don't
1.
understand why this is the n cubed versus
Yeah.
For positives greater than 1, that is true. You would be okay to establish that. But minus 1, that's not a bad idea. It's not a bad idea. Okay? You're right, it would work, but you would use the limit comparison test, which is way better than the direct comparison test in such a case. So I guess it would be a non-issue, really. This was one kind of problem, direct comparison to prove convergence. Let's use direct comparison to use divergence. Take a look at 1 over n minus 1, which you might think that's kind of like 1 over n. Let's establish how it relates to 1 over n. N minus 1 is less than n, so 1 over n minus 1 is greater than 1 over n. So the sum of all the terms of each of 1 over n minus 1 would be greater than the sum of all the terms of 1 over n, which is infinite. So the series you're asking about is greater than one known to be infinite. So it must be infinite. And the answer, or the conclusion, what do you reckon it's going to read like? The series diverges because it is greater than the series 1 over n, which diverges in y, C series, or just... Okay, that's the idea. Along the same lines, if you had been given 1 over n plus 1, n plus 1 is greater than n, but 1 over n plus 1 is less than 1 over n, it would be a non-starter or a dead end, because all it would tell you is the series you're asking about is less than infinite. So, okay, you follow? Okay, I guess in plain old English you'd say greater than infinite is infinite. Okay, why don't you try number 9 on tonight's homework? There it is right there. That's slightly changed from the book. That's what I want to get to. So try number 9. Do you conclude converging or diverging? Diverging. Series diverges because it is greater than the series 1 over root n, which diverges because it's a p series with 2 equal 1/2 plus 3 equal 2. That's direct comparison. You cool? Okay. Questions on sets? We're going to do tests tomorrow. Tomorrow's extra practice day, so tomorrow I'll do tests. Okay? How about questions on 127 replacement? Here's my answer to 7 replacement right there. The thought process behind it, I'll be happy to go into.
Wait, 7?
Yeah, what do you mean replacement?
It's at the end of this. It's at the end, sorry.
Oh, see, I hadn't gotten there.
Of course not, it would be on the backside.
Always finish.
Do you?
I usually, what the I've already got.
Wait, so you
Okay. Yes, it should be square, thank you. Yes.
forget instead of power step.
Because
Shred it.
the pedal would start at 0 and I want to go until it gets to its outermost point. And it would be at a max R when you take the sine of pi over 2. So 7 theta needs to be pi over 2. So theta needs to be pi over 14. Okay, I'm sorry, questions on this? 24.
No, I thought.
Other questions says 24. That's it? God, you guys are good. 10?
19, just how you say what it converges to.
Did they ask?
Oh.
You use your calculator and do, I typically will do maybe 100 or something. Okay, just you can use your calculator. There's no formula for pieces. I heard somebody, did somebody say 10?
Yes. Also 7, I'm just gonna get into it like the maximum.
Okay, 7 for
Same
both
thing
sides.
with 13.
And 13. Okay, cool, I can do that. That is a good skill for multiple choice tests and such. So, here we go.
That's usually.
Number 24.
So then it would be 1 over 3, 1.
Yeah, okay.
That would be what?
It's not replaced, right? Okie dokie. So, I think that there are 3 asymptotes. There are 2 vertical asymptotes at x equal positive and negative 1. And end behavior says that the limit as x goes to infinity yields that the function approaches 0. It's important that you make the jump to what does that mean? That means the graph approaches y equals 0 as a horizontal. So there are 3 asymptotes. There's also an x-intercept at 0. Okay, with all those x-intercepts and vertical asymptotes and horizontal asymptotes there, you can get a sign test. I think the graph is neither odd nor even, so never mind on that. Forget that nonsense. Let's go to the far left side. I'd have negative over negative. positive over here?
I didn't, that was just why, I forgot.
Okay. Around -1, that is a first degree, so it should change signs there, so I'll then go negative. If I get 0, that is also first degree, so it should change signs. And then after 1, it should change signs. So that, and then did I ask anything else? Okay. How about 10? Question on 10. 10. Uh-oh.
Because it really was so much.
Because somehow they got like
That was the, it's like the,
They got T?
how many did you?
What?
They got 1/13. Like,
Oh, so how did they get 1/10? Okay. Let's see. What did you go with U and DV?
I didn't do this side to this.
Okay.
B and C.
Okay. So DU is, oops, 2x. So DU is 2 cosine of 2x, and B is 1/3 e to the 3x. The first time through. So UV is 1/3 sine of 2x e to the 3x minus 2/3 e to the 3x cosine of 2x. So far, so good?
Yes.
Okay. So the next one through. So a little more room. You were consistent, so U is now cosine of 2x.
Yeah.
And dV is, and 2/3, did you bring it out front or did you leave it in with the?
I brought it out front.
Okay,
what? It's extra.
so, so then that's e to the 3x du is -2 sine of 2x. And v is 1/3 e to the 3x. So, that's unfortunate. UV, yeah, my handwriting's atrocious. So I get 1/3 e to the 3x cosine of 2x minus v du 2/3 e to the 3x sine of 2x. Sweet. Okay, I'm going to distribute 1/3 sine of 2x e to the 3x minus 2/9 e to the 3x cosine of 2x plus 2/9, 4/9, right?
Yes.
4/9. I imagine that's going to be where your 13 comes from, but we'll see. E to the 3x sine of 2x dx. So if I move that over, and combine it with one whole one in there, a whole one. Oh, shoot, this is a negative. I don't have that negative in there. My du is negative. This should be negative. Right? U is cosine, so du should be -2 sine of x. So this should actually be 1, 2, 3 negatives, and I feel like this 4/9 should be a negative term. And I bet that's where your mistake is coming from. Because now, when you bring it over, a full plus 4/9 is 15, 13/9. Does that do it? Cool. 7, back of the book versus my answer. So let me see the back of the book and your answer. Let's talk about how we can be sure that they coincide. If they coincide, maybe you made a mistake. Who's to say? 7. 7 is -2 cotangent t cosecant squared t plus 2. Right? Am I looking at the right one? Would you? That looks a lot different. Let's see. Let's see here. This will be fun. Okay, so -4 that's a 3 sine cube, right? Okay, so let's talk about this. Sine cube. This is sine. This would be 4 times 2 sine t cosine t sine t over negative sine cube t. That's a humdinger. All right, let's go. So 2. Let's see. What do I want to go with? Cosine squared minus sine squared? What are you thinking? For the cosine of 2t, there's 3 different forms of that, yeah? Let's go with, in order to cancel that bad boy, I'm going to go with 1 minus 2 sine squared version. You cool?
Yes.
Okay, cool. I love this identities. I love identities. All right. So these 2 of the signs drop out, and I get -8 cosine t over sine t. Sweet.
Yes.
Oh, this would be maybe -2 cosine t over sine cube t. Negative. And then positive 4 sine squared cosine t over sine cube t. Aha. -8 cotangent t, that's cool. Minus let's go with a 2 cosine t over sine t, and then a 1 over sine squared t. I'm trying to get that guy right there. Oh boy. And then we're almost done. This goes to 4 cotangent. Are we going to win? Let's see. -8 4 is -4 cotangent t minus 2 cotangent t times cosecant squared t -2 cotangent t. This would still be 2, and this would be cosecant squared. Aha! You are right.
Wow.
Isn't that fun? Yeah. All right, so we're cool. Your answer is 100% correct. Perfect. 13.
Same thing, it didn't look like the back.
Okay. Did this require 13 is like a. Oh, so this is algebraic cleanup on the second derivative. Is that correct?
Yeah.
Okay. So 13. Let me. Can you read it? Oh, I did some weird spacing with the boxes. Huh? Oh, that's right. Yeah, boy, I did not do well. 18. So I wonder if they subbed in. I bet they subbed in. Sorry.
Some of them are big, 18, but they're useless ones.
Some of them are massive and totally useless, and some of them are so small.
Like 18 was the most pointless figure.
Yeah, check out a quarter of the page.
Not bad.
No, I'm actually okay with that. Make like, feel free to make like extra big boxes.
I thought it was funny.
But no, we gotta do it. How about you just to make up space, we gotta cut some stuff.
Yeah.
Yeah. Okay. It was a lot. It was so much more work than the last.
Oh my god, what's that? I know, I'm just gonna switch 13 and 18.
I mean, that's, yeah, that's a good reason.
That is such a tiny box.
I'm coming. God, what you're slow.
I believe it is the same business of Is what? Oh,